So this brings us to our last organic chemistry. As far as naming goes, chapter 18 is more organic chemistry, but we'll deal with proteins and things of that nature. So this is just the naming of these fine chemicals, which I know each and every one of you are very excited about doing each and every day. You'd be like, oh, look at that. That's pentanol. Yes, very exciting. No, all right. But anyway, it is that naming classification. All right. So let's look at amines and amides. All right. We already know let's name them. All right. Amines are derivatives of ammonia, NH3. So they contain N attached to one or more alkyl groups. One or more alkyl or aromatic groups. Methylamine, a methyl group, replaces one of the hydrogen atoms in ammonia. The bonding of the two methyl group derives dimethylamine. All right, so if we look at that, let's look. Okay, so right here, and all right, so we've got ammonia, base ammonia, right? And we could probably build these. I believe Lisa is doing a lab tomorrow. Why don't you guys go crazy and make ammonia, virtually with the molecular models. And then we've got methylamine, right? And then we've got dimethylamine. And then here we've got trimethylamine. All right. So pretty straightforward, not too difficult, and if you look at the Lewis dot structures, okay, methylamine. All right. So we got that one grouping right there. Dimethyl. That one there, trimethyl, one there, and one there. All right, perfect. So aromatic amines use the name aniline, which is approved by IUPAC, which is always good to know that it's approved by IUPAC. Aniline is used to make fabric dyes, including indigo. And who doesn't love indigo? I'm just saying, it's fabulous. So, given the following name of the two amines, all right, well, so we've got our ammonia grouping, our modified ammonia grouping. All right, so what are we thinking? We got 1 and 2, right? So that would be ethylamine, right? Because ethyl, two in the backbone, right? And then our amine grouping right here. This aniline. Okay, so we got our benzene ring, all right, and our NH2 group there. So how does this link the environment? Alkaloids, amines, and plants? Alkaloids are physiologically active nitrogen-containing compounds produced by plants. They're basic compounds used in things like anesthetics, antidepressants, and stimulants. All right. So nicotine is a stimulant, right? Something unfortunately I'm all too familiar with. It increases the level of adrenaline in the blood, which also increases the heart rate and blood pressure. And me being a bigger gentleman, definitely the heart rate and blood pressure are an issue as a smoker. I'm guessing I'm going to try to quit smoking personally. But anyway, I am on blood pressure medicine, and I am on something to slow down my heart rate called a beta blocker. But this nicotine really works against that. So thinking, physiologically, if I were to reduce my amount of nicotine, all right, it would definitely help with my heart rate and blood pressure, all right? It's addictive because it activates pleasure centers in the brain. And anybody that has ever smoked and became a smoker knows that, the first couple times they smoke, they get all dizzy and lightheaded and kind of goofy. It does activate those pleasure centers, and you're always kind of going after that. That's what creates that addiction. Caffeine, yeah. Most people don't realize it's a drug, just like everything else, whether you like coffee or don't, Becca. Tea, things of that nature. All right, they all have caffeine. It's a central nervous system stimulant. It increases alertness. It's found in coffee, tea, soft drinks, energy drinks, chocolate, and cocoa. It's addictive because it activates pleasure centers of the brain. So people that are like, oh, don't talk to me in the morning because I haven't had my cup of coffee, they're actually telling you the truth because it does activate those pleasure centers. All right. Morphine and codeine, if you guys have ever broken a leg, had teeth pulled, you've probably taken some form of codeine or hydrocodone, such as Vicodin, things of that nature. So it's found in organal poppy plants. It's very addictive, highly addictive. That's why it's in prescription painkillers and not something you can just grab over the counter. It's structurally similar to morphine. All right. So morphine is used, unfortunately, to make heroin, which is strongly addictive and not used in medicine, but it used to be. It's similar into the structure of codeine, and then OxyContin is something that I remember actually being developed, before my time. Not before my time. During my lifetime, I had some major surgery in between my junior and senior year. OxyContin was not even a option until recently, or somewhat recently. It's a prescription drug used to relieve severe pain. It has physiological effects similar to those of heroin. So again, highly addictive. That's why people get addicted to these things, and that's what you can be cautious of when you're taking painkillers and things of that nature. Okay, so these are the chemical structures of morphine, codeine, heroin, and OxyContin. All right, so you can see that their base structures are very similar to one another, and it's derived from this poppy plant. Okay, they're opiates, so that's something you always want to be concerned with. Amides are derivatives of carboxylic acid. They have an ammonia group, or amino group, NH2 group that replaces the alcohol group in those groupings. Okay, so carboxylic acid, and then this is amide. All right, and we talked about nylon polyamide, so obviously it's got that amide functional group. All right. Amidation is the reaction of a carboxylic acid and ammonia, or an amine, the replacement of an OH group by an amino NH2 group. All right. So we've got propionic acid and ammonia. We had a little bit of heat, and we got propanoic sorry, and then we've got propanoic acid and methylamine. And we've got N-methylpropylamide, and that N represents the position. All right. So if we draw the condensed structure, well, what's going to happen here? Well, the NH3 is going to get rid of that OH, and it's going to turn into NH2. All right. See, same basic structure, but we kicked out the OH, and the NH2 took its place. So how do we name amides? Both IUPAC and common name amides are named by dropping the ic acid from a carboxylic acid name and adding the suffix amide. All right, suffix afterwards, prefix before, so suffix. All right. So we've got butonic acid. All right, and we're going to keep the buton. All right, and we are going to put amide at the end. All right. Easy as that. So let's get the following common name for the following compound. All right, so how do we do this? Remember, replacing the oic acid or the ic acid ending with amide. All right, so the name of propanamide, the common name of propionamide. All right, but what do we do? How do we get pro? 1, 2, 3. Okay, and then the amide at the end. All right, so organic chemistry, part 1. We need to know organic compounds. We know that they're carbon bonds. Normally in many cases, they're hydrocarbons, carbon, hydrogen, and then the addition of something else. And we've got basically our esters, alcohols, aldehyde, ketones, alkanes, alkenes, alkynes, aromatic compound. Aromatic contains the benzene ring. Carboxylic acids. So we got a carboxyl group. We have alcohols. Amines have nitrogen. Amides, okay, and then esters. All right, so this is a good little chart to keep us on track where we're at. You may want to chart it down and drop it down as the rules for each and every one of those. Remember, as you go to sleep tonight, meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. I'm sure you will dream of these names as you sleep tonight. I hope everybody has a good evening, and yeah, this is the continuation of the lecture we started this morning, and talk at you later.